Hi, welcome to our monthly webinar series. For those of you that are not familiar with us, we are the Center for Subsurface Energy and the Environment. We were formerly the Center for Petroleum and Geosystems Engineering. To learn more about us, please visit our new website, which is listed below. We are a group of faculty at the University of Texas at Austin. There are 24 faculty and principal investigators, as you see here. We collaborate with industry in many different ways. One of those ways is through industrial affiliates projects, and I've listed our IAPs here. I've highlighted two of those, the gas enhanced oil recovery and chemical enhanced oil recovery IAPs, because our speaker today, Kishore Mohanty, leads or co-leads both of those. More about our monthly webinars. They are intended to be informative, industry-driven webinars by researchers and collaborators in our center. Normally, we hold those the first Friday of the month at 12 p.m. via Teams, and all webinars will be uploaded to our YouTube page, although we hope that you attend these live. Some upcoming webinars, one of them is integrated fracturing, geomechanics, and reservoir simulation using a fit-for-purpose tool by Mukul Sharma. Here's the flyer we have for that. You can learn more about his talk on our website. And then in January, Zoya Haidari will be giving a talk with a title to be determined. So with that, I'd like to introduce today's speaker, Kishore Mohanty, who holds the Moncrief Centennial Chair Professor of Petroleum Engineering in the Hildebrand Department of Petroleum and Geosystems Engineering, and also the Center for Subsurface Energy and the Environment. Kishore received his PhD from the University of Minnesota in 1981. He worked in Arco Oil and Gas Company for 10 years before joining academia. He conducts research in Chemical EOR, Gas EOR, and Nanotechnology. He's been recognized by SBE for the Distinguished Achievement Award for Petroleum Engineering Faculty in 2016 and the Anthony Lucas Technical Leadership Gold Medal in 2013. So with that, I'll turn it over to Kishore.
Thank you, Matt. So I'd like to summarize some of the research we are doing over the last 5 years. Chemical techniques to increase oil recovery from shales. As you know, shales are very important to US economy. So about 60% of current US oil production comes from shales. But the problem is that it declines very fast, almost 75% in the first year. And the cumulative recovery after a couple of years is only less than 10%. So what can we do to improve it? That's the question we want to address today. So first thing, we got to ask the question, why is this primary recovery so low? There are, of course, several reasons. The first being this shale formations are extremely low permeability. Also, there is limited reservoir energy in the system. So when that energy goes away, the production goes down. And I have trouble getting my cursor in here. Okay. All right. So sometimes also as the pressure goes down, the microfractures close. So there is very little conduction over there. And sometimes the matrix next to the fractures get some deposits of organic deposits. And there is some frac water blocking. Okay. So these are the reasons why the primary recovery is limited. What can we do to improve this? So let's look at different strategies. So these are the reasons. So these are the things we could do to improve it. The first thing is mechanical. We can go refrac. In fact, Professor Sharma in our department does a lot of work on that. We work on chemical, a little bit on thermal techniques. In the chemical techniques, we can inject some gas like CO2 or hydrocarbon gases and do Huff-n-Puff. And a lot of people have tried this out now in Texas, and they see very good response to that. We have also seen that by using a chemical blend, such as some surfactants and some other chemicals in water, we can improve the oil recovery. And these chemical blends can take out organic depositions, clear out the frac water blocking, and in some cases can improve the permeability next to in the matrix next to the fractures. Also, if you can come up with some techniques to prop up the microfracture, that will also help improve the oil recovery. We have also looked into thermal aspects, like putting some microwave energy or radio wave energy, which can energize the reservoir and by in situ heating and improve recovery. Today, I want to give you 3 stories. First one as a combination of this gas and chemical blend. The second one is second and third one both are aimed at propping up these microfractures. So let me go through these one by one. If you have any questions, please put it in the chat box, and I would like to answer those questions at the end of the talk. So the first story is on combining this gas and chemical blend. We know that the gas can solubilize oil if the pressure is high enough. It gives also some energy to the system, so for the puff process. If you put some chemicals, it can alter wettability. It can promote spontaneous imbibition. It can reduce interfacial tension. These can remove the blocks, the water blocks you may have, and make the oil flow better. If you combine the two, you can use the gas to force the chemical into the matrix, deeper away from the fracture. So these sort of things should help. So the goal of this first study is to test this out in the laboratory. And this work was done by Tongzhu and Chen. So this is what we do here. We work with shale outcrops. Now, saturating these shales is very difficult because both the porosity and the permeability are very, very low. Okay? So we have to actually go through a process to put oil into this. So what we do, we vacuum the core samples for a couple of days. Then we put these cores into a pressure cell, and we surround that by oil, and we pressurize it to about 2000 psi. Then we raise the temperature to about 80 degrees Celsius. And as the temperature increases, this oil expands and tries to go into the pores. So the pressure actually goes up to about 7000 psi. We leave it there for about a couple of weeks, let the oil go in slowly. And after that, we depressurize and take the cores out. And we do in order to find the amount of oil we put into these cores, we both weigh them before and after. Also, we take T2 NMR before and after. So this is how we saturate the cores. To do the real Huff-n-Puff experiment, we do the following. We again have a pressure vessel, and we put a core over there. Then we inject either the chemical blend or the CO2 as needed, and we pressurize the CO2 to about 4000 psi at about 80 degrees C for about 3 days. Then depressurize at about 2000 psi, assuming that's the pressure the fractures see when you are doing the puff cycle. And we repeat this cycle about 3 times. Okay. At the end of that, we are done with the Huff-n-Puff. We depressurize, take the core out, and again weigh them and do a T2 NMR to see how much liquid did we produce and so on. So this is the material we're working with right now. It's a Mancos shale outcrop. It is mostly quartz and clay. We like to work with reservoir material. If some company would like us to work on them, I would love to work with the company with the reservoir course. But this is easy to buy, so that's why we are working in this, on this outcrop. So the chemical blend we are working with right now is basically we start with a KCl to brine. Actually, instead of water, we use D2O, deuterated water, because This one doesn't have any signature in enema, so we can distinguish from injected liquids to the reservoir liquids or the core liquids. And then we add half a weight percent anionic surfactant. We also add half a weight percent persulfate salt. So these salts actually reacts with the matrix and increases the permeability a little bit. It can also react with kerosene at high temperature. The surfactant removes the water block, and then we also use the CO2 for the Huff-n-Puff part. Just the chemical blend part was covered in this paper, and you can look it up. All right, so this is the result I want to show. What we do in oil saturation. So this is the NMR spectrograph showing the T2 distribution, and T2 is in x-axis in milliseconds. Y-axis gives you the incremental volume. The blue line over here is basically what you get from the NMR of a core that hasn't been treated at all at the initial state. When we do oil saturation, the blue line changes to this red line. As you can see here, there are two peaks. This peak is in smaller pores. That's why it's at smaller T2 time. The second peak over here is in larger pores. And this is where, when we do the oil saturation, this is where we are putting in some extra oil. This is actually kerosene in our experiment, a light oil. With this initial state before Huff-n-Puff, we do the Huff-n-Puff experiments. We have done many experiments, but I'm going to show you 5 experiments. Okay, so first one is a control experiment where we don't use CO2 or we don't use any chemical blend. We just heat it up and bring it down, see if there are any changes. Okay, so that's the control experiment. Second one is we do CO2 Huff-n-Puff. Third one, we do first inject this chemical blend, then do CO2 Huff-n-Puff 3 times. This one, instead of chemical blend, we just use brine or D2O in this case, and CO2. And the last one, we switch the order. You inject CO2 first, and then inject the chemical blend. And if you see here in this column, we have the initial liquid content from NMR. And we have this is in the next column, we have the liquid content after the oil saturation. As you can see, they have changed by a little bit. So this is the injected oil by subtracting this from that. So injected oil is of the order of 0.5, 0.6 milliliters. That's all the oil we can put in at this high pressure into these outcrop shales. So let's look at the control experiment, the NMR T2 distributions. The blue one is again the initial before we did oil saturation. The red one is after we did oil saturation. The black dotted one is after we did the control heating and cooling down. As you can see, the heating and cooling down doesn't change anything. So the black and the red one are pretty much the same. The difference is our error in measurements. So if you look at the volumes here, what it looks like. So before the Huff-n-Puff, we had 3.49 milliliters of liquid there. After the Huff-n-Puff is 3.44, pretty much the same. So this is basically our error in measurements. So now I'll show you our key 3 experiments. So we did CO2 Huff-n-Puff at 4,000 psi, 3 cycles. In this case, the liquid that came out was about, this is before and this is after Huff-n-Puff. The difference is how much liquid you produce. So it's basically 41% of the liquid that was there. So significant amount of oil can come out by CO2 Huff-n-Puff. When we do the chemical blend plus CO2, this number goes from 41% to almost 65%. So the chemical blend does help in changing wettability and increasing the permeability slightly near the fracture. And finally, if we change from chemical blend to just brine, so take the chemicals away, but put brine, this number again comes back to 40s. Okay, so chemicals do help and work synergistically with CO2 in recovering the oil. Now, if you look at them in terms of the NMR or the fluid distribution, this is for the CO2 Huff-n-Puff. What it shows is red is before the Huff-n-Puff, and the black dotted one is the after Huff-n-Puff. We make a big difference over here. This is the oil that we had put in that we removed by doing the CO2 Huff-n-Puff. But very little change in this section or in smaller pores. Whereas if we use the chemical blend, we also change that. Okay? And when you use water, we don't change that as much. It still is fairly high. So by adding the chemical blend and CO2, we are removing some liquid from tighter pores by this method. There is one concern though about gas Huff-n-Puff always. You have to go to pretty high pressure in order to get the oil out. And that needs big compressors and big compressing cost. So this is what we did in our first few experiments. So we injected the chemical blend first and then the gas. So how about we do the other way around? So where we inject CO2 first and then inject the chemical blend. If you do that, then you don't have to compress the CO2 to that high level. The chemical blend or even water can compress the CO2 or the last stage of compression of the CO2. So we wanted to see if this process works and still give you high recovery or not. So that's why we did this last experiment. So we injected first CO2 and then the chemical blend. Here, however, we did just one cycle, not 3 cycles. But even with this one cycle, we got almost 60% of the liquid out. So that tells us that this is also an effective process and can save some money in terms of compression cost. Here, this is showing the NMR, and this last one is this green line that also shows good oil recovery here and good oil recovery also here in smaller pools. So to close the first part, let me conclude. For shale oil EOR, CO2 Huff-n-Puff can be combined with chemical blend with pretty high recoveries. And again, we have been doing experiments with CO2, but we are looking into doing these experiments with hydrocarbon gases. That's what we're doing now. These chemicals in the chemical blend can improve oil recovery by doing a wettability change, which can improve imbibition into it, lowering IFT and increasing the permeability near the fractures. The NMR is a good way to evaluate these things with very small volumes, and pressurizing the injected gas by injecting the chemical blend or water first, but this after the gas, it is a good way to save some compression cost in the field operations. Now I want to move into the second story. This is on Micro-Encapsulated Acid, MEA for short. So let me actually show this picture. So when we do fracturing, we put in proppants. A lot of the proppants probably don't get to the microfractures, okay? Because either they settle out near the thing, and they're also too big to go into the very small microfractures. And if you put very fine proppants, they may go in, but they also flow back when you depressurize. So most of the time, these microfractures are unpropped. And then when we depressurize, pressure goes down, these microfractures close, so we don't get much production around them. So one way to overcome this issue is to make these fracture surfaces uneven with some acid treatment. Okay? And people do acid treatment, but oftentimes if you just use a bare acid, that leads to shale softening in some shales with a lot of calcite content and loss of fracture conductivity. There is also some issues with corrosion. So to overcome that, what we want to do is encapsulate that acid in some kind of package. Okay? So we make some droplets of these acids coated by nanoparticles. Okay? And so these things have density similar to that of water. And if you inject that, this is going to flow just like water and go into all kinds of pores and to the microfractures. And when the microfractures close, these are going to break. These little particles we have are going to break, release the acid, and that acid hopefully etches the microfractures. And so now it's uneven, so you'll have a permeability. So that's the idea we want to pursue and evaluate. So what we need to check out is that these encapsulated acids have good thermal stability, and they do release after when you break these particles. The way we do these experiments, we take these acids, which may be 15% HCl, and we take these hydrophobic nanoparticles and mix it in a blender. That's all we do. And what that gives us is this particles, encapsulated MEA. Okay, you can see it's like particles and it builds up. Okay, these things can be dispersed in water or in diesel or whatever you want to, and you can inject that. Okay. So this is what they look like. They are about 27 microns. We'll have looked at them under SEM and in microscopy, and these are particles about 20 to 40 microns, and they can really go into these small fractures during the fracturing process. And these things are pretty thermal stable. So this is looking at the stable of these MEAs, and this is at different temperatures at 80 degrees Celsius. Even after a week or hundreds of hours, they are pretty much there. Okay, so not much of these particles have broken up. Whereas if you take acid in oil emulsion, then in a few hours they break up. So their stability is not that good. So these MEAs are good long term. You can store them for a week and you won't have a problem. So then we also did a reaction with of these shales with these particles or these emulsions. And here we showed some of the data. So this is if you treat the shale pieces with non-encapsulated acid, bare acid. There's a lot of reaction, a lot of loss in mass in the shales. If you do acid in oil emulsion, doesn't help that much. If you take these MEAs and break them, you also react. But if you keep the MEAs intact, it doesn't react as fastly. There's a little bit of leakage, so there will be a little bit of reaction, but not very much. So then we do experiments with a fractured core. So we take a shale core and we fracture it, and we put in these particles into it, and we measure the conductivity of this fracture before and after treatment with this sort of chemicals. So that's what I will be showing you. Here is the conductivity. Oops, let me go back. Yeah. Here is the in yellow or brown over here is the initial conductivity of fracture, and this is the final conductivity after treatment with this sort of particles. So as you can see, the conductivity has increased quite a bit, almost 40 times in this particular case. And if you look at it, why the conductivity increased, this is what you see. Before the treatment, this is what the fracture surface looks like. After the treatment with 10% MEA, you see a lot of these holes, basically where the acid came out and reacted with the calcite and made a little pit or hole over there. Okay, so the surface becomes rough, and that's what we wanted to do. This is the roughness of an untreated shale surface, and this is after the treatment over here. So this is what gives rise to this high permeability. So conclusion from this second story is that we can micro-encapsulate concentrated acids in silica nanoparticles. And these MEA show good thermal stability, even at 80 degrees Celsius for a week or so. And these acids can be released when you crush them under the microfractures closing, and that releases them, and then they can react with the surface and increase the conductivity up to about 40 times. All right, so now I'll come to my last story, in situ proppant growth. This is again addressing the same problem as we were addressing in the last one. This is just another way. Instead of using acids, you could use this technique. So again, the proppants don't get to the microfractures, but we want to have some proppants there. The way we are going to do it, we are going to inject some chemicals which react with the shale surface and make proppant in situ right there. Right? So this is the idea. So we have the microfractures. This is shale. The black is the shale, and we inject in this chemical with our frac water, right? So it reacts with the surface and makes some proppants. So when you release the pressure, now we have within 24 hours this reaction occurs. We have now some local proppants over there which are stuck on one of the faces. So they'll stay there, and the fracture closes, but it will stay open to some extent, and that's what is going to give rise to conductivity of these microfractures. This is idea, if we can really develop it, could eliminate the idea of bringing all these proppants from far away and injecting dense proppants into the well bores. So we want some proppants which have a hardness, something of the order, something between the hardness of calcite and quartz. And we find that we can make proppants like that in situ by hydrothermal reactions. So, and this we have tested only on calcite-rich shales. Okay, so we have worked on calcite-rich shales. So this shale we are working with has calcite layers and also calcite islands in the matrix. And this is a calcite-rich shale, about 56% calcite. So the kind of experiment we do is the following. We take shale pieces, we react them with our chemicals. We want to find the right combination of the chemicals. We actually use two chemicals, this H and D. So we did some experiment with different combinations of these. And these experiments are named here 1 through 9. So we did 9 experiments like that. We did them in low salinity brine. We also did it in seawater. And in some cases, you made proppants, which sort of is shown over here in 24 hours. And we analyzed what the proppants look like. We also measured the strength. Okay? We want this surface to be strong so that it will stay open. So initial hardness of this shale is about 230 megapascal. We measure in each of these cases what the strength is and find the combination of the chemicals where it's good. We also do some fracture core experiments. Again, sort of we take a fracture core, find its initial permeability, and then we inject these chemicals, let it react, and form some particles, and then we measure afterwards we measure conductivity also and see if that improved. So these are some results from the batch experiments. As you can see over here, in this first experiment, the exact concentrations were given in that second last slide. We made pretty nice crystals of the order of about 500 microns, and also we made a lot of holes in the shale. Okay, so shale surface becomes uneven, and we are forming some crystals. This is experiment 2. Similarly, experiment 4, lots of crystals. Experiment 5. This is that was done in the low salinity water. This is done in high salinity water. Experiment 5, experiment 7. And here are some results. This result is basically the strength of the shale surface with the crystals that I have formed. Okay. So 230 is the base case where there is no chemicals. Okay. As you can see, if we keep both the chemicals about the same concentration, we get pretty hard surfaces. But if otherwise, the surfaces become weak. Okay. So this is how we choose what concentrations of the chemicals we should use. So something of the order of either 1% for both or 2% for between 1 and 2% for both the chemicals. That's what we want to use. Same here also. This is the result from the fractured core experiments. So we took those cores and we had these 2 reservoir cores here and 3 outcrop cores over here. And their initial conductivity in the reservoir cores was sort of a little bit high. This is millidarcy per feet. In the outcrop cores, it was less because we probably didn't have a good saw to cut the reservoir cores properly. These ones we worked with the cut surfaces that we got from the company where we got the outcrop core. After doing doing this reaction and making these in situ proppants, we saw the permeability in this case went up a little bit because it was already high to start with. In the second case, we see it's a significant increase, almost 10 times. Here also we see about 3 times, here about 6 times. And here is the surface that you see after the experiments. The fracture surface has lots of these particles, and that's what is propping these fractures open and is increasing the conductivity as shown over here. Right. So I'll now wrap up this section. As you can see, we can make proppant-sized crystals by injecting some chemicals and reacting it for less than a day or 24 hours. So we hope in the field we can inject these chemicals, and during the shut-in time you form these crystals and then you flow back. And by that time the crystals are formed, so the microfractures stay open. These we noticed that these crystals tend to form in calcite-rich regions because they react with the calcite. Proper design of chemical formulation can lead to good hardness for these generated crystals. So avoid the shale softening issues. The reaction is able to improve the fracture conductivity in some of the experiments we did of the order of 3 to 10 times. So with these, I would like to just post these references. So we have these papers related to this work that I talked about that you can read up in the literature. I'd like to thank all the peer collaborators that have worked on this, the students Tangzu, Robin, and Songyang, and 2 research associates, Krishna and Chami from our group. This initial work was supported by BHP, and these 3 people, Matt Honarpo, Doug Peck, and Ed Turek, worked closely with us, and I would like to thank them for getting us started in this area. A lot of the funding for this area has come from our Chemical EOR JIP and our gas JIP. So without this financial support, we won't have been able to do this work. So with that, I will stop and take any questions you may have. So the first question, did you do similar with natural gas versus CO2? That's actually the experiments we are doing right now. And we think if the natural gas has enough of ethane, propane in it, they would work fine. They would work very similar to CO2 if the pressure is high enough. If it's just methane, purely methane, then I think it will take a lot higher pressure. But with some ethane and propane, I think it will work very similar to CO2. Second question, is carbonate presence in shales required for MEA performance? Yes, absolutely. So here we are putting an acid, and that acid is going to react with the carbonate, calcite. So you have to have calcite over there to react and give that uneven surface. Okay. Third question, do you think that well retard acid blends will perform as MEA? Okay, so these retarded acids, yes, there are other ways people do. So one of the ways is to make an emulsion, right, with diesel. But what we showed that one of the slides, if you remember, that this nanoparticle stabilized particles are a lot more stable than diesel encapsulated emulsions. Okay? So we think this is a good way. This is really protects that acid, and it can only come out when you put that pressure and break these particles. So I think they are more stable in this case. This fourth question, can you mention the pressure applied to crystals per year? Yeah, so that the pressure that we applied to reported conductivity, we had about 1000 psi overburden pressure, something like that, right? Not too high. Any other questions? So I think using natural gas is very important because that's something that's available in the field, and might as well use it. And I think there are two mechanisms that are helping. One is the solubilization, the other one is just pressurization. And you can do both of these by CO2 and natural gas. So if people are interested, of course, in CO2 sequestration as a corporate strategy or something, CO2 is a good thing to use. Otherwise, natural gas is the thing to use because that's available right there. And we should be doing that. At what pressure do these MEAs break? They will break at very low pressure. So basically, if you, I guess one should figure out what that pressure is, and we don't know exactly. So we basically put something like 500 psi overburden pressure, and then it sort of closes, and these things break. But I'm sure it's going to break at a lot smaller pressure. As long as you sort of squeeze them too much, they will pop and release the acid. Injecting a water and chemical shell would be a challenge due to injectivity. So yes, so we are not really injecting a lot of water or chemical in this chemical blend. Okay? So it's really not. All we are doing is we are pressurizing the fractures and the microfractures with these liquids. That's all we are doing. We are putting them in these things, not in the matrix itself. In the matrix itself, it has to go in by some other mechanisms. So if this chemical you are putting is wetting the surface, then it can be imbibed in. So we try to add some surfactants that will make this water, sort of the shell surface, water wet, by which water can be imbibed in along with the chemicals. So yes, by just pressurizing, it's very difficult to put any sort of chemicals into it. Second, so there is a question now. Does the entire amount of chemicals consumed, or does some of it flow back? Right. So I guess it depends in what sequence we put it. I would guess part of it is imbibed into the system, and the rest of it comes back, flows back. And I'm presuming that this is related to the first part of the presentation. How are you planning to use chemical and gas combination dry if injectivity of water is challenging in shale rock? Yes, so what we are thinking right now is you should inject, let's say, CO2 or some other gas, and inject it to a pressure of, like, so let's say 2000 psi. And then you inject the chemicals to push the CO2 in. So CO2 would actually physically go into these matrices. The chemicals will not be going in by convection very much. Okay, but they would be compressing that CO2, increasing the pressure in the CO2 to 4,000 psi. So that way you are not using a big compressor, but you are using this liquid to compress the gas. But some of the chemicals in the liquid is helping you at the surface of the matrix and fracture. Do you think that 1,000 psi pressure applied to the crystals is really representative of the high stresses applied in the microfractures, especially in wells? Okay, so good question. I don't think so. We haven't applied a lot of pressure in our experiments, but we have measured the strength of these crystals, and it's in that MOH scale. It's in between that of quartz and calcite. So it has reasonable strength. So I think you'll survive the conditions in the reservoir, but we haven't obviously applied a lot of pressure that some of these fractures go through. Story 1, based on NMR compared with just CO2 injection. Seems like CO2 brine can move some fluid from small pores. Yes, that's what the NMR signature implies, that it did move some fluids from the small pores to bigger pores with the brine. And that will depend on what kind of wettability brine has to these pores and other things. Yes. Most of the conventional wettability altering surfactants would heavily absorb on the shale rock. Would it be economical? Yes, absolutely. Most of these surfactants will absorb, but we are really not pushing these chemicals deep into the reservoir. This is just a treatment of the matrix near the fractures. So I think you put a certain amount of chemicals, and you'll be limited by the economics. You don't want to put a lot of these chemicals. Yes. Did you try a more dead oil starting point to try and replicate a depleted shale SRV to see if you get a significantly different recovery versus more live kerosene oil? Actually, we have been doing mostly with kerosene, but certainly we need to try it with other oils. So we love to work with other companies who give us some of the field oils and the field rocks that that is of your interest, and we love to try them out both in dead and live conditions and see what effect also it has. Have you tried using enzymes instead of HCl on nanoparticle? Enzymes does not get consumed, and some studies have shown that enzymes can give reaction over the longer period of time when reaction is not necessary. That we have not tried. That's the short answer to it, but that seems like a good idea. Basically, you want a chemical that works slowly, not very rapidly like HCl. And by slowing down that reaction, you can sort of make some holes in some places, but not in all the places. If you do the reaction in all the places, the things fall apart, and you don't want that. Good question and good suggestion. Which class of surfactant would you recommend for wettability alteration on shales, non-ionic or anionic? So first thing you have to figure, you have to find in the surfactant that it has to be high temperature tolerant. Most of our shales are pretty high temperature, right? So it has to be high temperature tolerant. That sort of gets rid of a lot of non-ionics. So then basically the surfactant we used was an anionic surfactant. Conventional reservoir cores show lowest residual oil under the intermediate wettability conditions. Is this still true in unconventional reservoir cores? First quick answer is that we haven't done a lot of experiments in unconventional cores or shale cores because and get to the residual because it's so difficult to work with them. Okay? So we cannot easily sort of take oil out and water in or clean the cores, because once you clean the cores, you destroy the structures, the clay structures and everything. So it's very difficult to do sort of routine tests that we do in conventional cores in the unconventional. So it will be difficult to answer this question, but I think these cores also have a mixed wettability to start with. There are obviously organic regions which are oil wet, and there are inorganic regions which could be water wet. So you have, and so I think I cannot answer this question very well. What are the D and H chemicals? I assume it's not free to learn if a company would like to apply for in situ proppant growth. Yeah, if you we are still undergoing the patent. We have done I'm not going to disclose totally, but it's simple. D is basically some kind of acid, and H is a salt, so this controls this acid dissociation. Okay, so it's something like that. But if you would like to work with us, please come to us and we can work with you. How core surrounding pressure and core pressure difference influence the results of stage 2 and 3? Yes. So the pressure by themselves do not affect these reactions. Okay, so these reactions that are involved in these cases are, I think, independent of pressure. But some of the mechanical things like breaking of these particles, MEA, or the strength of these crystals we make, they do depend on pressure and needs to be studied more carefully. Why chemical use is very limited in shale EOR? Is it because of acceptance by industry or something else? I guess in our industry, you have to demonstrate very well and by field experiments, and then people accept it. And there hasn't been a lot of field testing done. So we were working with BHP, and we had a mini test type of thing, and that showed some good results. But before we could do a full-fledged test, BHP sold all their Eagle 4 assets to another company. So we didn't go through that. Do you believe EOR could be a next big thing in shale EOR? Well, to improve asset utilization. So I think this is something we need. And these Huff-n-Puff experiments are showing good positive results. But again, that's you get some increment. To make bigger increment, we need more new ideas. So I think we still have a lot of understanding to develop and processes to develop. Do you plan to suggest the use of MEA as a pre-flush for fracturing treatments in shales? I think it's a good idea. I mean, people do a little bit of acid flush sometime, right? So this kind of the acid flush, is going to affect your tubulars and other things, and having these MEAs, I think, could help. I think it's a good idea. You'll put some acids in some spots in these microfractures, which is going to help you eventually. Good question. I think this is an exciting area. We are doing some work, and we like to work with companies and work on specific. We have been working on outcrop cores quite a bit. It would be good to work with real field cores, with field oil, and see if these processes really work in the real system. How to make analogy of Huff-n-Puff in labs to fields, or why half cycle, why the half cycle is S? Okay. So I don't quite understand the question, but I think there is a good question I can make around it. So in the laboratory course, we see the oil recovery of the order of 60%, let's say. Does that mean in the field we are going to get 60%? No, of course not. Okay. So what we have to figure out is how far are the fronts of the whatever changes we make are traveling in our laboratory experiments, and how can we scale that up. Okay. So we have to better understand how these CO2 or chemicals are traveling within our course, and do some experiments in slightly bigger course and understand, at least in laboratory scale, like we right now use about 1.5 inch diameter cores. We can go to about 4 inches and see how the recoveries are affected, and then develop our theory based on that, which can be applied in the field scale. How much merit do you see for the lab testing of this technology? Do you suggest tests in the field? So I think all of these ideas need to be tested in the field. In the lab, we can, like I was saying, we can go from 1.5 inch to 4 inch, but that's about it. But then beyond that, we need some field tests to validate these techniques. Do you see a use of data analytics in EOR? Do you see a need of developing data analytics route to upscale lab scale experiments to field scale study? So data analytics has its place and will definitely help. So we did this. So let's say we do some experiments in the lab. It depends on what the mineralogy is. And so in that sense, you correlate with what kind of mineralogy you have and what sort of behavior you observed. And in the field, if you have better, more data on the mineralogy, you correlate your response according to those. So I don't see data analytics by itself is going to solve most of the problems. You got to combine the fundamentals with the data analytics, then you figure out what the scale up is. What is the relative size of the conventional proppants with the acid encapsulated proppants, assuming they are injected together in a mixture? This is important for crossing the acid infinite. Oh, so in the acid encapsulated MEAs, actually there are no proppants. Okay, we are just injecting acid that are encapsulated by very fine chemicals, these nanoparticles. These nanoparticles are too small. They are not like proppants at all. They are like 50 nanometers, whereas proppants are like hundreds of microns. So a micron is 1,000 times nanometers. So in the acid encapsulated particles that we send, there are no proppants. Okay. Okay, so I guess I answered that question. So when we are sending that acid there, what we want to do is we want to eat up a little bit of calcite on your face of the fracture and make a few sort of little holes there. So when the two fracture surfaces meet, there'll be lots of holes being connected, so it'll have some permeability. We are not actually making proppants in that case. In the third example, we did make proppants, and in that case, we didn't have this acid dissolution. How do you see the EOR in unconventional versus conventional in such low oil price? Actually, that's for the company people to figure out, right? I don't know the economics very well, okay? But I see some processes can survive even in the low price environment. All right. Thank you very much for these all these questions. I really enjoyed this webinar. So I hope we make more of these.